Hello everybody. I'd like you to join me on a trip through some physics. I recently purchased a book, Solid State Physics by Philip Hofmann, and I kind of felt like working through it and going into a little bit more detail perhaps, or elaborating on some of the concepts within it, using external resources and some of my own previous knowledge in physics, and try to put my own spin on the material and maybe present it to some people. Maybe we could go through it together. I'll be, providing a link in the description where you can purchase the book, and you can work through it with me. I'll be going through chapter by chapter, and taking each of the things within it, and hopefully learning this material and having some fun with it. So, again, this is Solid State Physics, Chapter 1. Chemical bonding in solids. So it starts out with the forces, attractive and repulsive forces, between two molecules. And an important part of this is the interatomic potential. Oh my god. I can't even do this. Atomic potential. It's kind of difficult to write on this pad. Oh, I tried to underline it. That did not work out too well. It's going to take some getting used to, some practice. Anyways, so they start out with a basic expression for the interatomic potential, which is written in the book as phi of r. That is the function. Is equal to A over Rn. That's pretty crappy R. Let's try again. A Rn minus B over Rm. So this expression it's obviously a very simplified expression. And it's an estimate, basically. Real interatomic potentials involve things like Schrodinger's equation and a lot of other complex math. But this is a very useful short equation for the bond between two particles. So, actually, I have a little demo on this. Okay. So I have the equation here, which is the black line. Let's turn off those other ones for now. This is the equation here. I simplified it a little bit by just having them both be A, the same number. They're usually going to be the same. In fact, I'll go into the full equation that isn't discussed in the book in a little bit. So we see there are two parts to it. There is the A over the x to the n. That is this part. Boom. So we see, just looking at this, let's zoom out a little bit, we see that this seems to have this like high steep path up here, and that would be representative of the repulsive force. So imagine you have a particle here at the 0 point, the origin. You have another one at 0.5. That particle is going to want to be pushed along this way. I kind of imagine like there's a ball. Imagine like a ball, put it here, put it at this point. What's going to happen? It's going to roll down the hill. It's going to want to go that way. It's being repulsed to the right. It's being pushed to the right. So the blue dotted line, the a to the x over n, a over x to the n, is the repulsive spot. And then we can enable the attractive spot. Whereas if you see only this line, you'll see if we put a ball here, it's going to roll inward. The molecule is being attracted to the other one. So we have both of them, the attraction and the repulsion, and when you add them together, you get this fancy little plot. And you can see that there is a curvature where there is a well right here, where this would be the most likely spot, or well, this would be the spot you should find, or the bond distance between the two particles. You can imagine one being at the origin, and pretty zoomed in. One being at the origin, the other one, part of the particle should be here. It's not a perfect model, but it's a good estimate. And again, through testing, you can get all these constants. I'll go into it a little bit more in a second, but this is part of the 6 to 12 rule for the x and the m, or 12 to 6. It's referred to as both ways. So, that is the basic equation that the book talks about. So, we have, let's see, let's get fancy and use these highlighters. Green? Blue. Okay, we'll do blue. So this one is the repulsive force. And this one, I guess we should. Let's do that. Cool. And this one, right here, I guess I should have written first. Save a little time, still getting used to this, I've never done something like this before, is the attractive force. Boom. Fancy as hell. Okay. Dang it. Alright. Again, this is a learning process. I hope you're enjoying this. So you can see everyone's human, and I'm a failure at writing with this pen tablet thing. Okay, so we have those two parts of the equation. Again, this is a super simplified model. So let's talk a little bit about where they get this from. There is an equation referred to as the, or it's not, it's a concept, I guess. There's multiple equations referred to as the Philip, oh wait, no, it's the name of the author of the book, Mr. Philip Hofmann. Thank you for writing this book. The Lennard-Jones Potential, which is basically where this was derived from. It's a little bit more detailed, and it has a little more flexibility, as you'll see in a second. But it's basically the same thing. Let's just start out by writing it. The V, the Lennard-Jones, that's what it's referred to, is 4 epsilon of sigma r to the 12th. This is where the 12-6 rule that I've talked about earlier comes in play. 6. So this is a, as you can see, they're pretty similar equations. This has some constants in front. Sigma is in place of the A, B, and then these powers. So, pretty much the same thing. And then there is another way to write it that is also very useful, and that is epsilon of Rm over R to the, oh, that's bad. That's just really bad. Let's try that again. Oh, I pushed a button on the pen. What's happened? Alright. Rm to the 12 minus 2 Rm R 6th. Okay, So these equations are, basically two different ways of doing this potential. And we'll actually use Desmos in a second, and you can see them in action and see why having these two different ones are useful, because you can adjust the equations differently and get what you want it more easily. If you're looking for the well, you'll see in a second. Anyways, so epsilon in this case would be the depth of the well. We have sigma is one of the things. This is the distance at which the potential is 0. We'll see that in a second. You'll understand a little bit more after you see the graphs I have. And Rm is the minimum potential. Minimum potential. So these equations basically, well, let's get fancy with the pens. Let's practice this real quick. Alright, green epsilon, blue sigma, sigma. Personally, I find the second equation a lot more useful, and you'll see why in a second. And we have the last one. We'll use yellow. It's probably going to be a little hard to see. Rm. And obviously, I guess I should write it down. R is the x value in the spot, or the distance. Distance from the origin. We'll just say R equals x. You'll see why in a second. Horrible. Whatever. Anyways, let's look at the graph. Okay. So here is the first one that we talked about. The 4 epsilon sigma I put as s. X, because x, R is essentially the x in a graph. R is just the distance away from the origin, so we're placing that there. And all this filled out. So you see pretty much identical type of graph. And you can, as you can see, the sigma here, which we talked about, we defined as the distance at which the potential is 0, is actually the distance at which the potential is 0. So 1.2, 1.2. This is where the potential is 0, and it's useful. It's useful to have that information. And then we come to the second equation, which is the one that's the epsilon and the Rm. I just put R here because R wasn't used. Rm over x, blah blah. You can look back. I'll pull it up in a second here. What's this equation? This equation right here. This beautiful one. And that would be this one. And instead of having the sigma, which shows the 0, where there's 0 potential, this one will show where the minimum well is. So this distance here shows where the minimum is instead. So basically you have these two equations, and you can use one to find where the potential is 0 and the other to find where there's the minimum of this graph. And probably this one would be more useful if you're trying to find the position of a particle in a bond, because this will be the estimation of that. There's probably some useful spots where finding this 0 point would be useful. None are coming to mind at this very second. Probably should have looked a bit into that, but I'll get better at that. But as you can see, if you were to line them up, they'd be the exact same line, just with different constants. Cool. So, what does this show us? it shows us that it takes energy to bond, and this would be the probable distance between the bonds. It's a very simple way to model it. So with the rest of this page, let's talk about the limitations. Because with equations like this, being huge estimates, obviously, you're going to be uh, limited based on the equation's complexity. Because if you were to do the actual, like, full mathematical models, it would take forever. Super complicated Schrodinger's equations. Solving past the hydrogen atom is a headache. So we use these simplified models just in order to estimate, get a good understanding of what's going on, and it works well enough. I mean, Newton's laws work where relativity is a lot more accurate version of that, but it's not really necessary to go completely into relativity for a lot of basic systems. So we're using basic systems here. So the first limitation is that this is a basic model, and it's an estimation. Secondly, I pushed the button on the pen again. Okay. Secondly, uh, this is basically only between two particles. Or it's only very accurate between two models, and I'll tell you why in a second. Because there is, based on this equation, you can see that there would be a linear increase in the bond energy. Whereas realistically, through testing, it's really a quadratic. Oh god, terrible at this. Let's write a little bit better. Increase. So that basically only is useful for two particles. Next up, we have that direction is irrelevant. This would be symmetrical around the atom. Direction is irrelevant, and it's symmetrical. And that isn't necessarily true, as you know. The poles and the position of the electron fields change, how the bond would work. But with this, that there's basically no way to distinguish direction. It's a distance from a central point, and that's really all you get. Distance from a central point around a single axis. So this is modeling anywhere. It doesn't represent all the forces. But again, it's an estimate. We don't need to put that. Just know that it doesn't really represent all the forces. And a big issue if you're into more of the programming aspect is that at 0, this is a divergent, which means it approaches infinity, which can cause problems with software and modeling. So just keep that in mind. You may need to do some modifications and look into that. I'm sure there's information online regarding that. Programming, if you're interested in programming that, or modeling that with some software. So that's about it for the first little section here, which was only about a paragraph, but somehow I dragged it out into a pretty long video. But well, it wasn't the best start, but I hope you enjoyed the time. Please come back and let me know what you think about this. If you're interested in watching more, I'm going to be making them for a while, and if there's some good response, maybe we'll go through some other books and learned some new things. So thank you for watching.